All right. Hey, AP Stats people. This is Mr. O'Connell giving you a quick overview on one specific chi-squared distribution problem from Chapter 26. AP Stats AP exam is coming up soon, and this is a pretty common one, so in case you need an extra example, here we go. As part of a survey, students in a large statistics class were asked whether or not they ate breakfast that morning. The data appears in the following table. Is there evidence that eating breakfast is independent of the student's sex? Test an appropriate hypothesis and give statistical evidence to support your conclusion. So one of the big giveaways that this is going to be a chi-squared distribution is that we have the two-way table here, and our data is in counts. It's not in percents. It's not in means. First, and that's actually the first condition, is that data is in counts. It doesn't say anybody was randomly selected or independent, but this is probably safe to assume. So data is in counts. Data is assumed to be independent. And another condition is that each cell is going to have at least 5. We have 66, 66, 125, 74. We can ignore the totals on that. In there, each is over 5. Instead of is over 5, has more than 5 entries. You also have to see if the 10% rule applies. In this case, there are 132 males and 199 females, both of which are less than 10% of all males and all females on campus. So 132 males, 199 females are less than 10% of all males and females on, I'm going to assume this looks like large statistics class, so I'm going to say on campus. I'm assuming large college campus at this point. So we may proceed with chi-squared test. There's 3 different chi-squared tests. This one, since it's asking for independence, you could just say proceed with chi-squared test of independence. There's also goodness of fit and homogeneity. I can talk shortly about this. The independence test is the most common on an AP test, which is why I'm focusing on it now. Degrees of freedom for a chi-squared, and it would be the number of rows minus 1 times the number of columns minus 1. In this case, we don't count the totals. 2 rows, 2 columns, each minus 1, so it would be a 1 by 1 or just 1 degree of freedom. So chi-squared is, start with the null hypothesis before I explain that. The null hypothesis when we have a test of independence is going to be that that there is no association, or that data is independent. So sex has no, sex is independent of breakfast. That if they're independent, that also means no association. Likewise, the alternative would be that they're not independent. I'm going to rephrase this, since sex doesn't really depend on male female doesn't depend on anything. It should really be breakfast is independent of gender. So I'm going to change that to is independent of gender or sex, or breakfast is not. In that there is an association. So in all to find a chi-squared statistic, I'm going to really tell you just use the calculator. But everything we did was always going to be chi-squared is going to be the sum of all of the observed values minus the expected values squared divided by the expected value. So I'm going to scroll out or scroll up really quick. All of these up here are the observed values. We need to find the expected values. So actually, I probably can draw it up here. Right here, if we make another box, male, female, this is, oh, hang on. There we go. This is breakfast, yes. This is breakfast, no. So what we have to do is look at the totals here. 100, we saw a 50-50 split here, but you see males is not 50% of the people that were surveyed. Males were only 132 out of 331, which is about 39.9%. I'm just going to round, we'll use 39.9. Why not? And then females were 199 out of 331, which is about 601. So when we do this, we're going to be looking at this proportionally. Since males only made up 39.9%, we're not expecting a 50-50 split between yes and no. So we're expecting 39.9% of the total people who said they eat breakfast, which was 191. Maybe if it's easier to just remember, you're finding the proportion and then multiplying it by the totals. So we're expecting right here, I think I had 76. Likewise, males still had 39.9% of the population, but out of the totals who said no, 140. That was about 56. I'm just rounding right now as well. Obviously, these are not coming out clean. So here, females were about 60% of the population times the 191 people who ate breakfast. So we observed 125, but when I multiply this out, I expected only 115. Finish up the expected matrix right here. Or I'm not even going to call it a matrix, just a two-way table. And that should have been about 84. So when you're now that we have our observed table right here, observed, we have expected. You're going to make two columns in the calculator on the table page, list them, and so it'll tell you once you hit menu, hypothesis test, and it'll say chi-squared, GOF. It stands for goodness of fit. It'll work in this case as long as you have the two columns here. Tell it what two columns you're reading it for, and it'll spit out a chi-squared. It'll spit out a p-value, and we'll make our decision from there. In this case, we have a chi-squared that's 5.16. And something to know about the chi-squared statistic, the larger it is, the more likely it is you're going to reject the null hypothesis. In this case, our p-value is 0.0231, which is generally pretty low. So at alpha level, let's call it 0.05, we will reject the null hypothesis. Remember, the null hypothesis up here is telling us that breakfast is independent of sex, and that there's no association. We just rejected it, so we're saying that there is an association. There is an association between sex and breakfast, with females more likely to eat breakfast.